little space.
All right. So for our next presenter, we have Mr. Darryl. He's with University of Texas at Austin, studying astronomy, and his research title is Stellar Properties as a Function of Position in the Praesepe Open Cluster. The floor is yours.
Hello, everybody. My name is Darryl. I'm a senior at UT Austin. I'm a double major in physics and astronomy, and my research mentor was Dr. Pereira. So I'll be talking about some of the properties of stars in the Praesepe Open Cluster and how they relate to position in the cluster. I'll start with some background of Praesepe and the background of how the information is attained. Specifically, I'll be talking about rotation. And then I'll take you through the steps that I took to do my analysis and some of the conclusions I came to, as well as my future research. So this is an image of Praesepe here. It's a star cluster in the Cancer constellation. Has about 1,030 stars, and they're pretty much small stars, young stars. It's an open cluster, and what that means is that the stars are very young, which means that since the ages are young, they're still main sequence stars, so we can get some very accurate information on mass and rotation because these things are very highly correlated when the stars are young. This next slide actually shows a picture that I took myself on the left side. That's a picture of the sun. And basically what we do is we utilize the spots on stars to get the rotation of stars. So these spots are tied directly into the magnetic fields of stars. So if you look at the picture on the left, you can take a look and see the sunspots, the dim areas on the star. And basically those spots are areas where magnetic fields are arcing in and out of the sun, and it looks relatively dimmer. If you look at the picture on the right, that's from a satellite, the Solar Dynamics Observatory. And you can see where the spots are, that's where there's a lot of activity going on. So basically the rotation of the sun causes the dynamos that happen within all the material in the star. These dynamos create these magnetic fields, and these magnetic fields output these spots that we can utilize to get the rotation of the sun by looking at the spots and seeing how they move. So this is actually not my work. This is from the paper that I got my data from Rampali et al. And what's going on is if you look at a star, the brightness of the star will vary according to the period of its rotation as the spots go around the face of the sun. So this is actually a reading or a capturing of the luminosity of the star as it goes up and down as the star rotates. And basically what they did was they took this period, this fluctuation of luminosity, they timed it over the period of several days. This is basically a 70-day reading. And they basically plotted these overlapping together, and the peak output the period of rotation for this star. And they did this they added 200 new categories of rotation for the stars in Praesepe, as well as confirmed a lot of the old rotation data. So basically, we were able to get more accurate measurements due to our new satellites like K2, Kepler-2, and Gaia. Now, getting into my analysis, the first thing I did was recreate a lot of the plots that's in that original paper to confirm that I had the accurate data, and also to confirm that I can actually maneuver the data. So this is actually my plot, but it's a recreation of a plot in the original paper where they took basically the rotation data they got from 3 different uses of the K2 satellite. And what they wanted to do, the Rampali team, was show that they can take rotation data over time and it's consistent. So over the course of 3 different years, they took 3 different readings of rotation amongst the stars in Praesepe, and they plotted them against each other. And you can see how the mainstay of the linear line in the middle of the plot is consistent with the fact that different readings of these stars gives the same rotation data over time. Now, what I did next was make various different plots of Praesepe to just get an understanding of what the cluster is like. It's basically an oval-shaped cluster that's sort of flattened, almost like a pancake. Several plots I did, 3-dimensional plots, plots and rotating it in different axes, just to get an understanding of what it's like. This particular plot, you can have an understanding of how rotation and mass is distributed. So the size of the marker is actually the mass of the star. And you can see the legend by which I encoded the rotation. The lighter colors are faster rotators. The number is smaller, which means that it's taking a smaller period of time to rotate. And the longer numbers are a longer rotating time. So basically what I was wanting to do was just get an idea of what's going on. In my initial assessment, it seemed sort of random. So what I did was I started to actually slice Praesepe into linear slices along the X, Y, and Z axis, so that I can try to find an overlap to see where there are regions of, for instance, the fastest rotation, the greatest mass. Now, I had some difficulties with this method because what I found was it was very difficult to overlap these slices. And there was a difficulty in the code whereby it was dropping off stars. Like the more slices I cut Praesepe into, I was able to, for instance, the number of stars would go down from 1,030 to 1,020. If I sliced it 15 times, if I sliced it 30 times, it would be less stars. And my mentor let me know that it's probably because I was manually slicing Praesepe. And he told me I should research coding more and get more into the libraries that can do this automatically. So I spent the winter break learning coding, increasing my coding skill, and I applied a SkyCore library to do the coordinate transformation for me. I still had some difficulty with the overlapping, but I was able to retain the data a lot better. And this is an example of showing how, even though this is a very broad view, it started to suggest that the distribution is not symmetric. My initial idea was that the more massive stars would be in the middle, and it would sort of just peter out from there, but it seems sort of randomly placed. What I did was, building upon my slicing code, I started to cube Praesepe. And what that allowed me to do was position cubes all throughout the cluster without needing to overlap any of the data, and get a more clear assessment of what is dispersed where. So my first analysis was about 8 by 8 by 8 slices, and it gave me a similar distribution to the previous plot. But what I did was, as I got better at coding and I started to get a higher resolution of code, this is a slice where I sliced Praesepe into 50 slices along the X, Y, and Z axis, which gave about 125,000 cubes. So an interesting thing I noticed was, when I picked out the fastest rotating stars, there's no fast rotating stars in the center of Praesepe. All of them are just about the center of the cluster, from the center of the cluster to the edge, and a sort of ring around the cluster. So I found that pretty interesting. Whereas mass is sort of, you can find massive stars all throughout the cluster, the fastest rotating stars are sort of a ring around the middle. So that started that was the first indication that there might be some patterns to how the properties of these stars are distributed in the cluster. The next thing I did was, and it's important to mention that each step of the way I was increasing my code, building upon the previous analysis. So what I did this next analysis was, I took my cube code and I stretched it into radial slices, where I can actually slice Praesepe into a bunch of radial spheres of different distances. Now, the first thing I did was I set it so that I can slice Praesepe into thousands of slices, trying to get a higher resolution. But basically, that was essentially looking at each star individually. And it was difficult trying to find the right amount of slices to give me the right amount of resolution to see some kind of pattern. So what I did was linked upon my cube data. And since I sliced Praesepe into 50 by 50 by 50, I actually sliced Praesepe into 25 and 50 radial slices from the center. And what I found was, on the ninth cube, so this is the ninth radial shell, there's a dip in the period of rotation at about 17 parsecs from the center of mass. So I noticed that there's a pretty much linear drop in the rate of rotation from about 10 days to rotation to 5.65 days per rotation at 17 parsecs. And that seemed pretty interesting, that there was this linear drop, and then it became pretty random after that. I started to look more in depth into this slice and into what could be causing this. And I started to look more into the types of stars, because Praesepe is an open cluster. It has a lot of young stars, and it has a lot of small stars. So what these designations are, these refer to the different types of stars. Like an M star is the smallest type of star that we have. The largest type of star we know of is an O star. So Praesepe is filled with a lot of small stars. And what I found was that this shell is dominated by M-type stars, which are very small, and they have a broad range of rotation. So I suspected that maybe it's because there's so many M-type stars in this particular shell, but there's actually other shells that has a higher number of M-type stars. even though this is the shell that has the second highest ratio. Right? For every 4 M-type stars, there's one of the other type of stars. So what I intend on doing next is doing some more analysis to where I can find out what's going on, including looking at the spectral type. So this is a plot basically of the rotation period of the stars by the mass. The spectral type is encoded in the color of the marker. And what I noticed was that if you look at this area here, 5.65 was the area where there's a dip in rotation, and there's a large absence of stars at the 0.8 solar mass range. So I suspect that might be significant as well. So my next step is to look more into the rotation, more into the mass. I'll do a statistical analysis to see what's going on, to try to figure out why this is there, if it's significant, as well as codifying my cube and radial analysis, because the two types of code I found very much difficult in trying to combine them separately, like after the fact. So what I'm going to go do is go through all of my code, try to consolidate the radial and cube from the start, and see if I can figure out what's going on with the discrepancy in that dip, as well as apply the same analysis to multiple clusters. And what will happen is that if we can figure out what's going on, it'll help us with modeling clusters, understanding the life of stars, how things change in the cluster. For instance, if there's a lot of currents that's affecting the stars, that's affecting the orientation of the axes, that'll help us model stars and understand the life cycle of stars, as well as the process or the decay of rotation over time. So I appreciate you all coming, and you can let me know if you have any questions.
Any questions?
So you found here that the farther the star is from the cluster, the faster it spins, right?
Not necessarily. So these stars here are mostly M-type stars.
Yeah.
And the thing about these stars is they have a very broad range of rotation. They go from under 1 days for rotation to up over 40.
Okay.
So it's not necessarily that farther away rotation gets smaller, because rotation, the rate of rotation spans the entire range. It's just that the average rate of rotation here is lower, is a minimum as far as the entire range of distance. So, what I tried to do is to try to find a resolution that output a pattern that allowed me to see if there's some kind of relation between distance and rate of rotation overall. And what that might do is give us an indication of, for instance, because the way these stars get their rotation is from the collapse of these large gas clouds. And these large gas clouds collapse, and the momentum of the movement of the cloud is retained in the rotation of the star. So perhaps this might tell us something about how these clouds collapse, so we can model them better and better understand the evolution of these systems over time.
So continuing on, would this type of study be a good jumping off point to understanding like why the gravitational aspects of why things rotate, or is it just purely about the collapse of the gas cloud?
I wouldn't say it would help understand why things rotate. It'll help to understand how that rotation is translated into the life and existence of a star and a group of stars. Like, how does that rotation translate into what we see and observe in stars today? And basically, even though this is far into the future, but for instance, one of the things that we understand is that if a cluster has different stars have different axes of rotation, just like the planet, and some clusters, they're very much aligned. And some clusters, the stars are rotating in all different directions. I imagine that one day we'll be able to visit these clusters. It might be far into the future, but I imagine we can get the technology there. This might help us understand what the region is like. Like, is there a lot of turbulence in that area that's causing, that might be difficult for us getting there? Yeah. Even beyond just modeling what's there, but what's it going to be like when we get there? What's the environment like in that region? And this type of research will help us understand that.
Cool, man.
Thanks.
Can you go back to slide 6?
Yes.
Yeah, so what's the difference between this graph and the next graph after it? This.
Well, this graph is simply pointing out the areas in a very rough estimation of slices of where the average lowest period of rotation is and the average highest concentration of mass is. So you can say that this slice was an indication of the fact that, like, this is one of many graphs where I was just graphing things just to understand what does it look like, how is it shaped, where are things positioned at, in general, where is rotation at, and of course here you can't really see any kind of rhyme or reason. It looks just mixed up.
But in slide 7, did you ever look at that just like weird gap between the big blob and that like straight strip? Do you see that?
Gap between the
So
Around Z0.
yeah, like if you go to Z0
okay
and right on the right is that straight strip of stars that kind of cuts off from that
Like
big
in the middle,
blob.
yeah.
right here.
Yeah, you ever looked into that?
It's just the way the stars are placed.
Okay.
Yeah, so it looks kind of odd because we're looking at this from one perspective, but those stars are not necessarily right by each other. Like one star can be here, one star can be on the other side of the cluster, and that's just the way they're situated.
I get that, but like, do you think there's a correlation on why they kind of, because the data you're modeling here is like, do you think there's a connection to why they all kind of decided?
I haven't looked into that, but that's something I could look into.
Yeah.
In other words, why does there seem to be such a tight clustering in this area?
That's so far away from them.
Yeah, I haven't looked into that, but that's something to keep in mind. Thanks.
Okay. Well, thank you so much.
Okay.
Oh,
Oh,
Is
and
there time for one more? I don't know.
yeah, go ahead.
I just on slide 9, all the data points all had the same error. It was like plus or minus 1 parsec. Is there a reason they have the same error?
oh yes, because I actually, when I slice Praesepe, I slice it into even slices.
Okay.
So basically, the way I code up the program is send it on 17,
Yeah.
and then one less than that and one more than that makes one spherical shell, and I captured that shell. Can I capture just one more? Did you have a quick one?
Yeah, I was just wondering what determines different star types.
So what determines the different star types is the size. So the bigger stars have the O type, the smaller stars have the M type. That'll deal with the temperature, that'll deal with the color. So all of these things are included in what we determine to be spectral type, and we just put a letter on a grouping of those characteristics. Large, hot, big is an O, small, cool, M.
Okay.
Thank you all.
Thank you so much.
Thanks.